Hey guys, Mr. Riz here to help you out on the first part of the 2.2, let's say that again, the 222 part one, and we're going to be looking at data representation. So in this section, we're going to be looking at just like the little bit of data, and that's kind of a pun in itself. So our goals here is to make sure we understand or can explain how all the data is represented using bits, and to use programs and how to use programs used to translate into representation into easier to understand. So we'll learn about what a bit is and how a program can use that to translate it into other things. And then we're also going to use or understand why binary is used in computing and how we can translate that to decimal and vice versa. A good resource here is this Ascii table here that we will look at later on that converts binary values, maybe, or even, I forget, we'll open this up here. Oh yeah, we have the binary or the decimal and then what symbol and description it is. So we'll check a look at that resource later on, or you can Google some of those things too, and that kind of helps out. All right, so let's talk about data representation. Have you ever wondered how data is stored on like an electronic device, like how a picture can be saved on a phone or music can be played on a mobile device, or how our images, the sound and videos and other formats are translated into just the digital world? Devices use tiny electronic components called transistors to store this data. These transistors can hold signals that can be either one of two states, either on or off. If the signal is on, the value of the transistor is considered to be 1. If the signal is off, it's considered to be 0. Because of this, there's only two possible values we can have, 1 or 0. And so this is called a binary number system. So numbers we use every day are called decimal numbers. And they're called decimals, and the deci here would be 10 because there's 10 digits we use. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 of them. So how can a computer store such complicated decimals just by using ones and zeros? And the way that they can do that is by, we'll zoom in a little bit more, is by looking at the possible combinations of a binary digit. So if we have a 1 bit, so basically one source of information, there are only two possible combinations that it could be, a 0 or a 1. Now, if we multiply that or add another bit to it, so if we have 2 bits, each bit can be of 2 combinations, so 2 times 2 would result into 4 different possible combinations. We can have a 0, 0, a 0, 1, a 1, 0, or a 1, 1. Way that we can figure that out is we can take 2 to the second power, and that's how many combinations we would have. So how many values could we have with 3 bits? Well, 2 for the first, 2 for the second, 2 for the third, and we just multiply those all. 2 times 2 times 2, there'd be 8 total combinations. And so it raises a lot higher. So computers use a combination of these bits for allowing more values to be stored. So even though a bit is the smallest unit of data storage, it's the most common unit of storage in modern computing right now. It's a collection of 8 bits called a byte. So having 8 bits allows for 2 times 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 2, or 2 to the 8th combinations, which comes out to be 256 different combinations. And you can see those all could be written right there. So how do we take that, what a computer can read and understand, to make 1 byte, which is 8 bits, and how can we convert that into our number system? So humans use the decimal numeration system, or also known as base 10 number system, and we use that to represent our numbers. This is likely originated from the fact that we have 10 fingers and 10 toes, and this is just kind of what we think we made when we started counting. So each digit is a base of 10 numbers, can hold up to 9 values. So we can recall from the decimal system below that each digit here we can look at. And normally we see this number here and we think 4,692. And the reason why we do that, and we got some math here, but I've kind of taught math before, is we can always break down these numbers and what they mean. So, and this will help us when we start doing converting later on, is that 4,629, we can break it into 4,000, or 4 times 1,000, and 6 times 100, and 2 times 10, and then 9 times 1. Now we can actually convert these all into base 10. And then what I'm saying here is that each digit here does represent some power of 10. So 4 times 1,000 is really 4 times 10 to the third, And 6 times 100 is 6 times 10 squared. And 2 times 10 is just 6 times 10 to the first. And then 9 times 1 is technically 9 times 10 to the 0 power. So we can use that technique later on to help us convert from bases going back and forth. But we're so used to seeing those numbers that we don't think of that like in that format there. We just go through and look at that number and understand based on where it's placed, kind of like what that represents, how many thousands or 10,000s or hundreds do we have. Okay, so the binary number system can work the exact same way. Its position is based off what power we have. So if we look at a binary number like 1010111, we can look at that and start working backwards. Now what I like to do is, let me get organized here, is I like to put a little bit of exponents up here. Now starting from the right here, we got 0, 1, 2, 3, 4. So the highest number we got here is 1 times, now our base is binary, so not going to use 10, we're going to use base 2. So we got 1 times 2 to the 4th. We have 0, 2 to the 3rds, 1, 2 to the 2nd, 1, 2 to the 1st, and 0, 2 to the 0. So if we evaluate these all, okay, that's 16, 0, that's 4, that's 2, and that's 0. We can add them up, and so 10110 turns out to be 22 in our base number system. So let's try to do some math here. So what number is equivalent to 101101? Okay, so let's start with our exponents. 0, 1, 2, 3, 4, 5. All right, so we got 1 times 2 to the 5th. We got 0 times 2 to the 4th. 1 times 2 to the 3rd. 1 times 2 squared. 0 times 2 to the 1st, and 1 times 2 to the 0 power. We're going to figure out what all those are individually and add them up. All right, so 1 times that would be just 1. That'd be 0. All right, we got 4 here, got 8 here, got no 16s, and we got 132. And we can add those up together. 32 plus 8, that's 40. We got 44, so we got 45 in that problem there. You know, I should probably type these answers in. Make sure we are, got my answer key set up. Okay, next, let's convert all these here. So not too bad. These are all base 2s that we're going to convert to decimal. So we got 0, we got 1. So we basically have, the first number is 1, we have 1, and then we have a 2. And so 1, 1 would turn out to just be 3. All right, what about 0, 1, 0, 0? So we would have no 0 or no 1s. We'd have no 2s, and we'd have 1, 4. And so that number would just be 4. All right, what about the next one here? Kind of working backwards here. So let's see, how many 1s would we would have? A 1, and then we have no 2s. We'd have 1, 4, and we'd have no 8s. Yeah, and then 1, 16. So we add them up, 16, 20, 21. And then what's this last one here? Oh man, all these 1s here. Let's see, we would have 1, 1, 1, 2, 1, 4, 1, 8. Oh man, I'm already losing track. 0, 1, 2, 3, 4, 5, 6, 7. All right, so what is that? 2 cubed. All right, 116 with the 4 through the 5th power is 32, to the 6th power is 64, to the 7th power is 128. So let's see, how much would that all be? 128 plus 32, what's that, 160? That's 224. Oh man, I'm already getting mixed up. We'll add that in there. Is this 255? I believe so. Okay, so that's the highest power we could get. Okay, so given our calculations from the previous step, what's the largest value a single byte can hold? So a single byte would just have 8 digits, all being 11111, which is that what we did right above this? 1, 2, 3, 4, 5, 6, 7, 8. So the highest number we could get is 255. So even though there's 256 possible combinations, the highest value we can get is 1 less than that. Okay, so how do you think larger numbers could be stored in computer, aka multiple bytes with different programming languages using different numbers? So many languages represent an integer using 4 bytes. So given 4 bytes to store an integer, what's the largest integer value that can be stored? So we have 4 bytes here. 4 bytes would be 8 bits each, so we got 32 bits. So can we think the largest number possible? And so take a second here, maybe do the math, grab a calculator. So if we got 4 bits, each of them have 8 bytes. So 4 times 8, that's 32 bytes. So each byte can be one of 2 combinations. So what's 2 to the 32nd power? That is a lot of numbers here. So what's 2 to the 32nd power? Hey, Google, help me out here. There we go. Let me copy that over here. And then let's paste that into our quiz here. What is that? Let's see, hundreds, thousands, millions, billions, 4,294,967,296. Would be the amount of combinations, but we need to subtract 1 from that. There we go, that should be our answer. I put the comments in for all right, so what do you think happens to the program language with a 4-byte integer tries to calculate or store an integer larger than that? So we can see. Basically, we'd get a program that would crash into larger. So languages can use a fixed number of bytes to represent an integer limit, the range of the integer values, and the mathematical operations for those. So when a program attempts to store a number outside of that allowable range, a phenomenon called the overflow occurs. So specifically, an overflow error is an error that caused when a computer attempts to handle numbers that is outside its defined range of values. We might have done this too like before, but typically we have increased overflow values, so it's good. You might actually use this like on an old school calculator. In fact, like usually there's a limit that it will go up to, and then you just get a stack overflow error, where basically you're using numbers that are too big for the memory to even handle. All right, so different languages can handle overflow errors differently. So Python is not a language that uses a fixed number of bytes to represent integers. So this means that it can store sizes of integers that can change, and the range of the integer limited is only limited by the available memory of the computer. So if you wanted to go through and like evaluate like so many digits of pi, using a program like Python would actually be more efficient than trying to use something like, you know, a graphing calculator, because you're using the computer's memory versus like a calculator's memory. So what do you think happens when a programmer tries to program and calculate an integer larger than that number in Python? Well, it's not limited by that, so it will just go through and work with it. So let's go through here and start looking at how do we go backwards? How do we take our numbers here and convert them into binary? So let's look at a number like 9. How can we convert that into binary? And there's a couple different ways here. Now, when we look at a binary chart like 9 here, I kind of think of this as like making change. All right, so if you think about, I have a change drawer. I have 2 to the 0 power. I have 2 to the 1st. I have 2 to the 2nd. I have 2 to the 3rd. I have 2 to the 4th. I have 2 to the 5th. And technically, we go on forever. So we think about it, if we have $9 and we needed to break them up into here. Now, okay, this would be 1, 2, 3, 4, or no, 1, 2, 4, 8, 16, 32. Okay, so if we wanted to go through here and I wanted to make change for 9, we try to think, okay, what's the largest number I could give them? And okay, 16 would be too big. And so I could give them one of these 2 to the 3rd powers. All right, so that'd be $8 taken away. So I only have $1 left. And I would have 0 of these 2 to the 2nd powers. I would have 0 of these 2 to the 1st powers, and then $1 left, I'd give them one of those. So 9 converted into binary would be, all right, 8 plus 1, or in this case here, 1001, which was what we wrote here. Now I kind of work vertically, they do it kind of horizontally. So how could we convert 71 to binary? Okay, so let's think, you know, we might make our chart here. We're going to do 71 here. Let me go ahead and clear this off here. Let's keep this going here. We'd have to make our chart, our drawer larger, right? We got 2 to the 6th power is 64. All right, 2 to the 7th power is 128. Okay, that's bigger than 71. So we start, okay, so we'd have 164. Okay, what's 71 minus 64? How much is left over? That would be $7, right? Yeah. All right, so we'd have 0 32s. We can't give them a 16, can't give them to an 8, but we could give them a 4, right? So we could subtract 4 from that. Okay, there's a 3. All right, can we give them a 2? Yep, we can. So we can subtract 2. We've got 1 left over. We can give them a 1. So the binary number of 71 would be 10001111. All right, so let's try to convert these other ones here while we have a couple minutes left. So take a second, look at these here. We're converting these base numbers into those conversions. All right, so let's start off easy with 2. 2 is actually not too bad. We just want to make sure we understand this here. All right, so 2. All right, highest number here is 2, so we could give them a 2 in response, and then we'd have nothing left over. So 2 would actually be 1, 0. All right, what about 6? Okay, so 6, we're going to kind of start over here. You know, we'll just write this here. All right, 6. Okay, we can't give them 8. We could give them a 4, and then we could give them a 2, and nothing left over. So 1, 1, 0. All right, what about 15? Okay, can't give them a 16. We could give them an 8, which gives us 7 left over. We could give them a 4, which would give us 3 left over. It could give them a 2, which gives us 1 left over. And so 15 would be 1, 1, 1, 1. All right, 32. All right, we could give them a 32, which means we have nothing left over for the rest. So we have to continue to the rest of the chart here. So 0, 0, 0, 0, 0. So 1 with 5 zeros after it. And what about 250? Okay. 256, okay, that's the highest. Okay, 2 to the 8th power is 256. All right, so let's see, kind of going through that here. Changing colors up. All right, we would give them 128. So 250 minus 128. That would leave us with, what, 122 left over? Okay, we could give them a 64. So we could subtract 64 from that. And let's see, take that 112. Let's see, what number is that? Just trying to do the math in my head real quick. That's 58 left over. Okay, so we can give them a 32. All right, so give them a 32. That's what, 26 left over. Okay, can I give them a 16? We sure can. So 16, subtract, that's 10 left over. All right, can we give them an 8? We sure can. All right, subtract 8, that's a 2 left over. Can't give them a 4. We can give them a 2, and can't give them a 1. So it would be 1, 1, 1, 1, 1, 5 ones, 0, 1, 0. All right, so I'm going to type these in. Hopefully my answer key is all set. Good thing to double check here. 1, 1, 1, 1, 1, and then 5 zeros. 1, 2, 3, 4, 5. And then here, 5 ones. 1, 2, 3, 4, 5, 0, 1, 0. Okay. So now that we can convert from binary to digits and back and forth, we can also look to see how can we convert these to our standard characters. So we want to look at here and think about, like, in the early 80s, this character known as Ascii became the standard data representation for our computer system. It allowed us for non-numerical characters to be represented using basically predefined numerical values. So in Ascii, that use 7 bits to represent 2 to the 7th power, or 128 unique characters. But it was later extended to 8 because we have more than 128 characters that we can put on a keyboard. There's definitely more. So they got 2 to the 8th power, or 256 characters, which included some Latin characters and other special symbols. So we got this table that we can always go back to as reference for us to go through here and try to figure out what these values are equal to. So you guys are going to convert this table here into ASCII. So let's figure out what this binary digit is. Okay, so it's a decimal version of this here. And so we'll go through this kind of quickly here. I only got a couple minutes left before I have to get going. But you guys can probably see here, okay, what do we got here in binary? We got 0, 1, 2. All right, so we got 2 squared, which is a 4. And then 3, 4, 5, 2 to the 5th power is 32. We can add those together. Okay, that's 36. So that's the decimal equivalent of that. So we will look at our chart here and look, see what's the decimal equivalent of 36, and that is the $sign. So we'll type in the $sign. All right, so same thing here. Okay, the next problem. All right, let's convert this here. Okay, we got 2 to the 0 power is 1. 1, 2, 3. Okay, we have a 2 to the 4th power, which is 16. And 2 to the 5th power, which is 32. Let's add those two together, or add those numbers together. So we got 9, was that 49? All right, so that's the decimal equivalent to it. We look at the table here. All right, what's 49? 49 is the number 1. So that represents the symbol 1. Okay, what about this next one here? All right, what does this represent here? So we got 0. So we got a 1, and then we got 1, 2, 3, 4, 5, 6. All right, 2 to the 6th power is 64. So that's 65. All right, so we can go through here, look at our chart here, 65, scrolling down, 65 is the uppercase A. All right, so complete that table here. I think you guys can be all right. Now, how do we convert high to binary? So we have to go through here and actually look at each one of these symbols by itself. So we have the capital H, lowercase I, and then the exclamation point. So looking at our chart here, where is the capital H? All right, capital H here is right here. I'm going to just copy that in here, paste it. All right, then look for the lowercase I. The lowercase I, where is it? Scrolling down. All right, here's all the lowercase i's. All right, there's the binary number of 105. Paste that in there. And then the exclamation point. Where is the exclamation point? What number is that? Is it up here? Oh yeah, it was right one of the first ones here. Control C, and that is 33. There we go. So we convert that to binary. Okay, so this pretty much wraps up the lesson here. You guys can complete the table. I'll make it so you guys do a little bit on your own. But basically, the standard here is kind of represent. So although Ascii is one of the original standards developed for character coding, it's not the most common standard used today. Most commonly, standards used called Unicode. Unicode is a multi-byte character coding that converts most of the world's languages into writing systems, including modern and historical scripts, as well as multiple symbol sets and emoji characters. So Unicode is very popular, especially with applications that support multiple language. Pretty much Ascii was just really good for English languages. All right, so you might have been wondering how an electronic device can tell whether a specific binary number represents the actual number or a non-numerical character. So in other words, how can a computer tell if the binary number 01000001 stands for the integer 65 or just the letter A? And so the simple answer, it depends on the context that the binary is in. So it is up to the software application to distinguish the character between integer 5 or the character A. And so we can kind of take a guess on how that does, but basically we will look to see like what the binary value is doing. Like, is it being added or is it being like worked together? So if a programmer had to write all the code using binary representation for most modern day programs, they just never would be written. They would take literally forever. So removing all this detail, you can just write the letter A on your keyboard instead of writing out 010001. And so this is a level of extraction where we remove all those details there and we work on something higher. So hopefully this gives you guys an idea of what the binary system works. Then we're going to talk about later on, okay, how do we transmit all these numbers too? So go ahead, submit this in when you guys get done, and I will see you guys next for part 2. Have a good one.